Hi all, in this video I'm going to talk about moment distribution method that we use for analyzing indeterminate beams and structures. So far, you learned how to analyze a beam which is stable and determinate. When we say analyze, it means calculating the support reactions and draw the shear force diagram as well as bending moment diagram for the beam or the structure. So, as you can see, the top three beams are stable and statically determinate. It means that you can calculate the support reactions using equations of equilibrium, which are sum of the moment about any points equals to 0, sum of the force in vertical direction equals to 0, and sum of the force in horizontal direction equals to 0. Using these three equations, you can calculate three support reactions. So, for example, for this cantilever beam, we have three support reactions: bending moment, shear force, and axial force. And using those three equations, you can calculate all three, and then you can draw the shear force diagram as well as bending moment diagram for this beam, and the analysis will be completed. Same as the middle beam and the last beam in the first row, which are all statically determinate and stable. So if you remember, we discussed about the stability. For being stable, we need at least three supports or support reactions which are not concurrent and they are not parallel. So these three are stable and determinate. However, if you have extra support reaction, so instead of having three support reactions, which is compulsory to be stable, you have four. So as you can see, we have cantilever, which was stable already, and we added extra support, which is a roller at the end. So as you can see, this structure has four support reactions, and by knowledge that you already have, you cannot calculate these support reactions because you have only three equations of equilibrium and you have four support reactions and four unknowns. And same as this one, which is a continuous beam, we have if we consider that the axial force doesn't matter for us, we have 1, 2, 3, 4, 5 vertical support reactions. And you can also consider the horizontal ones that will come to 10 support reactions in total. And we only need 3. So this beam is statically indeterminate. Same as this beam with 2 fixed ends, and we have 3 at each end and 6 in total. So this row, they are all indeterminate. And with the knowledge that we already have, we cannot analyze these three beams. In the real life, most of our structures are statically indeterminate because we prefer to have extra support for our structure, which decreases the deformation and deflection of the structure. So we benefit from that extra support to decrease the deformation of our structure. And also you don't have to build the strong, like you don't have to choose a stronger beam or a stronger, bigger cross section. If you compare this cantilever with this fix at both ends and you apply point load at middle of these two beams, the deflection at the middle of this cantilever is much higher than the deflection in the middle of this beam with two fixed ends. So as you can see, as a structural engineer, most of the time we prefer to have indeterminate structures. So it is important to know how to analyze an indeterminate structure using manual calculation and analysis. So we can go through this and try to see if you can find out if these structures are determinate, indeterminate, stable, or unstable. Okay. Now we want to see how we can analyze an indeterminate beam. So this method that we are going to learn is the moment distribution method. So before I start teaching the method, I want to talk about what the philosophy behind this method. So if you consider, I share a whiteboard with you. So let's say we have a very not a straight beam with let's be generous, put more supports. Okay, let's say we have this beam, which is obviously indeterminate. We have 3, 1, 1, and 3, which comes to 8 support reactions, and we only need 3. So we have 5 degree of redundancy. So it is indeterminate and stable. So in order to analyze it, we need to use a method that we don't know yet. So in order to use moment distribution method, what we are going to do in this method is to fix each joint, each important joint. When I say important joint is a joint that something physically happens to the beam or the structure. So as you can see, if you exclude or ignore the loading, so we are not going to talk about the loading at this stage, just the structure, the physics of the structure. For example, if you have a support, it is the place that we consider for fixing it during the process. So ignoring the loading that we have, so let's say we have UDL here, we have point load here and whatever. So it doesn't change anything in what I'm going to talk about. So in this method, at the joints, the important joints that the physics of the structure changes. For example, where we have support, we consider that we put a fixed support at those joints to keep it rigid and see how much bending moment this joint will get. And to make it easier, we have some pre-calculated tables to find out if we apply this force in the middle of this beam, how much would be the bending moment at both ends. So we use that table and we consider these joints are locked. When we say locked, we consider they are rigid and they cannot rotate, and we calculate the bending moment at those joints. And then we unlock it or release it. So when we say unlock or release, it means in the real case, we don't have any fixed support here. So the beam allow to move or rotate, so it is not fixed. So we have to release it. When we release it, the bending moment that we already calculated at this joint needs to get distributed along the beam. So first we lock the joint, calculate the bending moment at each joint, and then release it and distribute the bending moment that are at that joint. So this is the philosophy that we are going to use in this method, which we also call it lock and release method, okay? So let's go back to what we were talking about. Here. So in this method, the sign convention is different. So when we say sign convention in this method, it will be on the right-hand side, the clockwise is positive, and on the left-hand side, clockwise is positive. So as you can see, clockwise will be always positive, and anti-clockwise or counterclockwise is considered negative. So it is very important to keep this convention all through the method. Do not change this convention at all, because then the result will not be correct. So we have some ingredients for this method, or factors that we need to calculate or find before we can use this method. So we have these four factors that you need to calculate. Then you can use this method easily. So one of them is stiffness factor. The other one is distribution factor, carryover factor, and fixed end moment. This is not a factor, as you can see, because we are talking about moment. It depends on the loading. So to calculate the stiffness factor, we consider two cases. One case is when we have far end fixed or far end continuous. When we say far end, it means you have to calculate this stiffness factor at each joint for each member. So when you stand at A and look at member AB, the other side of the member is B, which is the far end. So when you're writing KAB, it means you're standing at A, so you write A. You're standing at A and look at B. So here, as you can see, B, when you write the letter B in the second letter, it means it is your far end. So look at joint B. Is it fixed end or is it a continuous beam at B? Then KAB will be 4EI over L. So as you know, E is modulus of elasticity, I is moment of inertia for that member, and L is the length of this member. The other case is when you stand at A and the far end, which is B, is a roller or pin support, which is the end of your beam. So as you can see, we have a pin support here, but the beam on top of that is continuous. So in this case, you have to use 4EI over L, but in case that the far end is pin or hinge and it cannot carry any moment, you consider 3EI over L. So you have to calculate the stiffness factor for each member at each joint. So for example, if you look at this beam, you have to calculate KAB, KBA, KBC, and KCB. So we have 4 stiffness factor that we need to calculate for this example. Then we have distribution factor at each support or at each joint. For calculating the distribution factor, we have dF equals to K over sum of the K, which means at each joint, the distribution factor of that member at that joint equals to what you calculated here. For example, if you want to calculate the distribution factor for BA, you have to write KBA divided by KBA plus KBC. And similarly, DF, which is distribution factor for BC, equals to KBC divided by KBC plus KBA. And when you add KBC and KBA must be 1, because we want to see how stiff are these two members at this joint. And we distribute the bending moment depending on that stiffness. And also, if you are at each joint, you are at a support. If it is fixed and support, and the distribution factor equals to 0. And if you're at the roller or pin support, the distribution factor equals to 1. The carryover factor, which is another factor that we need to calculate, it depends on, again, the situation that you're calculating that factor for. For example, if you're calculating the carryover factor at A, it means if you apply a moment at A, half of this bending moment will go and carry over to joint B. And again, if you're standing at A here and apply a bending moment, the bending moment which is transferred to the other end, if it is fixed, it is 0.5. So for fixed end and the continuous end, if you're staying at A and look at the other end of the beam and it is continuous, the carryover factor would be 0.5. However, if you're standing at A, look at the other side of the beam and it is pin or support, and there is no continuous beam after B, it means your carryover factor must be equals to 0. The carryover factor at each support also need to be determined. For example, for fixed end, we have 0. This must be carryover factor. COF for A equals to 0, and COF for pin end is 1. Okay. Then we need to calculate fixed end moment. So as I said before, we have a table that we can easily read the bending moment from this table depending on our loading and our supports. So if we have one support, fixed support, and one roller, and we are applying a concentrated or point force in the middle, the bending moment at the fixed support equals to 3 PL over 16. P is the value of this point load, L is the total length of this beam divided by 16. So you can easily calculate the bending moment at that support. Or if you look at this both end fixed support beam, you will see if you apply a point force in the middle, the bending moment at both ends are equal to PL over 8. The important thing that you need to pay attention to in this case is, as I said, the sign convention is clockwise positive. So as you can see on the right-hand side, the bending moment is clockwise, so it is okay, it is positive. However, on the left-hand side, the bending moment that this table gives you is anti-clockwise. So if you are going to use this value, you must consider minus PL over 8 because it is anti-clockwise, and in our convention, in this method, anti-clockwise is negative. So you change the direction to clockwise and use minus PL over 8, similar to this one. So if it is anti-clockwise, you change it to clockwise and consider the value as negative. Let's have a look at an example. So if we have two end fixed with a UDL 12 kilonewton per meter, from the table, the fixed end has WL squared over 12. So that would be this case. We have two end fixed support with UDL. So the bending moment is WL squared over 12. As you can see on the right-hand side is clockwise positive. So we write it as is. However, on the left-hand side, because in the table it's anti-clockwise, we change the direction as clockwise and consider minus the value, which we calculate 12 times L squared, which is 8 squared over 12, which gives 64 kilonewton meter. So sign convention is very, very important. So if we look at these examples, you can pause the recording and try to find out about the fixed end moments. Okay, I assume that you paused it, went through it, and here is the answer. So for this case, you must find 3 kilonewton, which is positive and clockwise. For this case, again, 3 kilonewton clockwise. And for this case, we have minus 3.5 because it was opposite direction as the table. And for the other side, 2.5 kilonewton meter. Here is another example that we want to see for this example, how we want to calculate different factors. So as you can see, we have one end fixed support at A. We have a pin, which as you can see, we have a continuous beam here. There is no internal hinge here, so it is continuous. If it was an internal hinge, that would be another story. So, and here we have a roller and one UDL and one point load. As you can see, I, which is the moment of inertia for this AB, is IAB, which means don't worry about the value, just consider IAB, and for BC is 3 times than IAB. Okay, let's see how we calculate the different factors. And also, as you can see, EI is constant all through the beam. First step is to find the stiffness factor for each member at each joint. So we are not calculating the stiffness factor for A and C because they're always the same, and we always use them to calculate the distribution factor. So you don't need to waste much time to remember or worry about memorizing the value for these two, for K, which is the stiffness factor. Just focus on other joints. So if we ignore the end of our beam, the only joint that we need to worry about would be joint B. So we have BA, so KBA and KBC that we need to calculate it. As you can see, if you stand at B and look at A would be your far end and is fixed. So you need to use 4EI AB over L. And for KBC, you stand at B and look at C. And C is your far end and is a roller. So you need to use 3EI over L. So if you simplify that, that would be 0.4 EI and 0.6 EI. Then we would be able to calculate the distribution factor. So distribution factor at A or AB is 0 because it is fixed end. And distribution factor for BA equals to KBA, here 0.4 EI AB, over KBA plus KBC, which in this case is 1. So 0.4 over 1 is 0.4. And for DFBC, we have 0.6 EIAB over 0.6 EIAB plus 0.4 EIAB. And if you simplify it, that would be 0.6. And for point or joint C, and the distribution factor equals to 1, which is pin end. As I said before, the distribution factor at each joint must be 0. So if you have distribution factor for BC and BA, if you add them together, must be 0. So you double check if your calculation is correct or not. So it's 0. Next step is to calculate the carryover factor. As I said, the carryover factor for AB, because A is a support, is 0. So as you can see, the carryover factor is the same as fixed and distribution factor. And for carryover factor for BA, because far end is fixed, is 0.5. And for BC, because far end is roller, is 0. And CB must be 0 as well. So I know that I didn't change it in the other slide. So here, when I was saying here, that was COF. COF must be 0 at both types of support. So if you have fixed end, is 0. If you have roller or pin end, is also 0. Okay. And then we have fixed end moment. So if you look at this, we consider that if we lock joint B, we have AB, which has 2 ends fixed, and we have BC, which is fixed at B and roller at C. So for AB, that would be which case? That would be this one, because we have 2 fixed supports at A and B, and the point load is applied somewhere along the beam. So A is 6, B is 4, and then you can calculate fixed end moment at B, which is PA squared over PA squared B over L squared. And for A is PB squared A over L squared. And as I mentioned before, for A, you need to change the direction and consider minus for the value. So for AB is negative minus 9.6 using the formula, and for BA is positive 14.4. And if you fix this joint and look at BC, you will see that this case will be similar to this one. We have one fixed support, one roller, and we have UDL on the beam. So the bending moment at B in this case would equal to WL squared over 8, and it is anti-clockwise. So we need to change the direction and consider minus in front of the value. So that would be minus WL squared over 8, which is minus 28.125. And fixed end moment at C, because it cannot have any bending moment because it's a roller, is 0. Again, in this in the table, we can see there is no bending moment applying at a roller because roller cannot carry any bending moment. Okay, that was the introduction about the factors or ingredients that we need for this method. And we will talk about it more in the class and how we can use these factors to proceed the method and analyze our beam using this method. Thank you very much for watching this video. See you soon. Bye.